In this video, you'll learn how to build a multi-agent industrial AI system and implement communication between the agents using the agent-to-agent or A2A protocol. Step by step, I'll show you how to break down a monolithic AI agent into multiple specialized AI agents, implement the A2A communication protocol, and standardize the way your agents exchange data and collaborate. Before we dive in, let me show you a quick demo of the finished project, and then we'll go through exactly how to build that. So I've built 3 AI agents: an equipment monitoring agent, a material calculating agent, and an orchestrator agent. Each AI agent implements the A2A protocol, and I also have a user-facing application that acts as an A2A client. With this setup, I can interact directly with the equipment monitoring or material calculating agents, or send a query to the orchestrator, which delegates tasks to the other agents and returns consolidated result. All of this happens through standardized communication with the A2A protocol. My name is Kudzai Mandi Teresa, and I regularly publish tutorials on industrial data and AI right here on this channel. So if you're new here, make sure to subscribe so that you don't miss any of the future videos. This is part 5 of a 5-part series on how to build agentic AI for industrial systems. So if you're jumping in fresh with this video, don't worry, I'll give you all the context you need to follow along in this video. All the code for this tutorial is available on GitHub. You'll find the link in the description below. Okay, so let me quickly describe our demo scenario for this tutorial. So we're running a simulated batch plant that mirrors a real facility, 3 storage tanks for raw materials, a mixer to combine them per recipe, a reactor for the chemical process, and a filler that packages the finished product. All real-time signals from the production equipment are exposed through an OPC-UA server. In a previous video, we built a single industrial AI agent that monitored this plant. It read live data from the OPC-UA endpoint to check tank levels, machine statuses, and it queried timescale DB database for product recipes to calculate raw material requirements, and then be able to answer questions like, can we produce X batches of a given product? Now, instead of relying on one monolithic agent, we're decomposing the work into a multi-agent system. Instead of one agent doing everything, we're creating 3 specialized agents. First, an equipment monitoring agent that specializes in real-time data. It connects to our OPC-UA server and knows everything about tank levels, machine states, and operational statuses. Second, a material calculating agent that specializes in product knowledge. It connects to our timescale DB database and knows all about product recipes, material requirements, and batch calculations. And third, an orchestrator agent that coordinates the other 2. When you ask about production feasibility, the orchestrator knows which specialist to consult, how to combine their insights, and how to make the final decision. Now, these agents don't need to know each other's internal implementation. They communicate through agent-to-agent or A2A protocol using standardized messages. Let me briefly explain how Google A2A works so that you have the relevant context to follow along this demo. The agent-to-agent protocol, or A2A, is a standardized framework that enables AI agents from different vendors using different models built with different frameworks to communicate and collaborate seamlessly. Think of it as a universal language for AI agents. Without A2A, if you have agents built with LangChain, AutoGen, and Crew AI, they can't semantically interoperate with each other. Each uses its own communication format. A2A provides the common language they all understand. A2A follows a request-response model similar to how web APIs work. A client agent sends a request and a server agent responds. Now, here's the interesting part. Any agent can be both a client and a server. So your equipment monitoring agent serves data when asked, but it might also need to request information from other agents. The protocol defines 5 core capabilities. First, standardized message formats. All communication uses JSON RPC 2.0 over standard protocols like HTTP or gRPC. This means agents exchange structured, typed data that any system can understand. Second, dynamic discovery through agent cards. So each agent publishes an agent card, which is like a business card that says, I'm the equipment monitoring agent, I can provide tank levels and machine states, and here's how to reach me. Other agents can discover these cards and automatically know what capabilities and skills are available from what agent. And then third, it has got built-in task management. A2A includes task orchestration, so agents can say, I'm working on it, and provide updates as they progress. And then fourth, multi-modal data exchange. Agents aren't limited to text, they can exchange sensor data, graphs, maintenance reports, even video feeds from inspection cameras. And then lastly, security and asynchronous communication. A2A includes encryption for sensitive industrial data and supports real-time streaming updates using server-sent events. Okay, so now that you've got a brief understanding of what A2A is all about, let's go ahead and look at our multi-agent industrial AI architecture based on A2A. When a user asks, can we produce 4 batches of product A? The request goes to our orchestrator agent, which exposes an A2A server endpoint. The orchestrator maintains an agent registry listing all agents it can reach via A2A. Using this registry, it discovers each agent's capabilities by reading their agent cards from a well-known endpoint. So it knows the equipment monitoring agent can provide material availability and machine status information. It knows the material calculating agent can provide production requirements. The orchestrator delegates tasks based on what's needed. It might ask the material calculating agent what materials are needed for 50 batches of product B. Simultaneously, it asks the equipment monitoring agent what are the current tank levels and machine states. Each of our AI agents exposes an A2A server endpoint, and so to talk to those agents, the orchestrator also runs its own A2A client connections. The equipment monitoring agent connects to an OPC UA server and retrieves real-time data, while the material calculating agent queries the database and calculates requirements. They respond to the orchestrator with structured data through A2A. The orchestrator combines these insights, applies business logic, and provides the final answer to the user. Okay, so let's start with the big picture of our project structure here. So at the root level, we have our main A2A project folder. And then inside it here, you see we've got 3 key different directories. So we've got the agents directory. So this is where our AI agents live. And then we've got the app directory. This is the application layer that users interact with. And then we've got the shared directory. This is what we have as our common resources and the A2A protocol implementation. And then here we've got our environment configuration and the requirement files for our required Python packages. Okay, so let's unpack our code starting with the shared directory. So here we've got the models folder, which contains our A2A data models. So basically our models here define the data structures as per the A2A specification that all our AI agents use to communicate in a standard manner. So if we open up the agent.py module, so this module is a definition of how an A2A compliant agent should represent itself and announce itself in the A2A ecosystem. So as you can see here, it includes a class for agent capabilities, which define how an agent should represent its capabilities. So as you can see here, we've got the streaming property. So here it is used to indicate whether an agent is able to handle streaming or not, and then push notifications, and then state transition history. And then we've got another class that defines the metadata about the agent skills. So basically an agent skill is what the agent is capable of doing. So as you can see, this class includes the ID, the name of the agent, the description of that agent, and then the tags, optional tags to categorize what the agent can do. So in this case, the name, the ID could be provide material availability, and then the name could be provide current material availability, description, and then examples of how these agents could be queried, right? And then you have got the input modes and the output modes, so whether it supports JSON, text, or whatever modalities it supports. And then we've also got the agent card. So this is what we spoke about earlier. The agent card is like the business card that describes the agent's capabilities. So when the agent first connects or first accesses the registry, it will get the URL where it can then start interacting with the AI agent. So the agent card contains all of that information. It contains the name of the agent, the description, the URL, where it is reachable, and the version, which is 1.0.0, and it also lists its capabilities, which are these agent capabilities here, and then it also lists the skills, which are the skills defined here. And then let's move on to the JSON RPC module. So this code here defines the best classes and structures for JSON RPC 2.0 messaging, which is the underlying protocol that A2A uses for communication. So here this includes the JSON RPC message, and then we've got a JSON RPC request, what it should look like. We've got the JSON RPC error, JSON RPC response, and we've got the internal error. And then we've got the request models. So this module defines the structured request models used in the A2A protocol. So these models basically represent the different kind of requests an agent might send or receive. So this includes sending a task or receiving a task. And this is all adhering to the JSON RPC 2.0 format. So as you can see here, this includes a class for sending a task request, a class for sending getting a task request, and then you have got an adapter, and then we've got a send task response, and then get task response. And then finally under models here, we've got a task. So this is the module that defines all the task related models used in the A2A protocol. So primarily in our demo, we're using tasks as a way to exchange messages between all these multiple AI agents. So here we've got a definition of all those task related models. So here we've got a text part, which is basically represents a part of a message that goes along with the task. And then here I've got a representation of a message, and then the task status, and then the actual task parameters, and then the task send parameters. And then here I've got an enum type that holds all the different task states from submitted, working, input required, completed, cancelled, failed, or unknown. Okay, so now let's go into the A2A folder. So basically this folder contains our implementation of Google's agent-to-agent protocol. So here I've got the agent registry. So basically this is where every AI agent that joins that A2A network or ecosystem needs to register themselves. So this could be hosted in the cloud or whatever registry you're using. So in this case, we're using this file basically to list our AI agents. So this one is our equipment monitoring agent, and then this one is our material calculating agent. So I've got two agents registered here in this registry. So basically the registration here, you're specifying the host name of that particular agent. So as you will see later, an AI agent will use this host name to then append that well-known address where it can then be able to access the agent's card, which lists all the capabilities, the skills, and the URL where the agent can then be able to interact with that specific agent via A2A. And then just here we've got the discovery module. So basically, again, this is a shared utility module that any AI agents, any of our AI agents here can use to discover the capabilities of the other agents. So basically, as you can see here, it is accessing that registry, and then once it does that, it loads the registry, and then it pulls those agent cards. So it will list the agent cards of all the AI agents that are registered in our agent registry. And then here we've got the client module. So basically this defines a Python client for interacting with an A2A server. So here basically, as you can see, we've got an A2A client error, an A2A client JSON error. So and then here we've got the main interface of the A2A client. And then here we've got a method of how our A2A client can send tasks to the server. It can get tasks, and it could send a request. And then here we've got the server. So again, this is also a simple A2A server implementation that our AI agents would then be able to also use to implement A2A server. So it supports, again, the ability to be able to start a server, get agent cards, handle requests, create a response. And then finally, in our A2A directory here, we've got a task manager. So basically, this module defines how tasks are managed in an A2A protocol. So as you'll see later here, again, we're going to use each of our agents is going to implement this class task manager or in-memory task manager to be able to provide that bridge between the Google A2A tasks and the actual execution by the agent. So again, here it defines how to upset a task. On send task, what should happen? And then on get task, what should happen? Okay, now let's have a look at the code for the actual agent. So if we go here, you see we've got the equipment monitoring agent, material calculating agent, and then we've got our orchestrator agent. So if I open this equipment monitoring agent here, so here we've got the main Python function. So basically, this is the function that is responsible for starting our equipment monitoring agent. It runs it as an A2A server at port 002. And then here we instantiate the agent card. We specify what the skills this agent is capable of. So as you can see here, this is a material availability and material states ID. This is a tool for providing material availability and machine states. The description, it replies with material availability and machine states. And then we've got the text, and then here are examples of how this tool could be used. So what is the current material availability in tanks and the status of production? Or it could be give me the status of production equipment and material availability. So this is what the AI agent that discovers this agent card is going to see, and then know exactly how it could use this AI agent. And then here we've got the agent card that then puts together all the skills, capabilities, and all this information about the AI agent, and then we start the server. And then here we've got the actual AI agent code. So maybe before we look into that one, first of all, let's look at this module, which is an Office UA data access. So these are basic Python functions for reading an Office UA server. So again, here you see we've got the server endpoint, and then here I've got the node IDs for all the tank levels that I want to read, and then the machine statuses that I want to be able to read. And then I've got an enumeration type here to determine the machine states. And then here I've got a class for an Office UA client. And then I've got these methods, basically, which is get material availability, which is basically an LPCUA request to get the material availability using those node IDs. And then we've got get machine states, which is again an OPCUA request to get the machine states using those node IDs. So what we're doing is basically we're taking these Python functions and then we're mapping these to LangChain tools. So we're using LangChain as the framework for this specific AI agent. So again, so this module is responsible for mapping those tools. As you can see here, I'm importing these two methods from our Office UA data access module. And then here I'm specifying this as a get material availability tool, which is mapped to this specific function, get machine states tool, which is then mapped to this function. So we've defined our data access layer. We have mapped those two tools. And then now we go into our main AI agent. So again, as I mentioned, this is a LangChain AI agent. So as you can see, we're doing a bunch of LangChain imports here. And then this is specifically a tool calling agent that we are importing here. And then first of all, here we're loading our environment variables, which include the API key for our Claude LLM model. And then here we are using this, we're creating a model of the response. So our response, we expect it to be structured in this way. It should contain the machine states, material availability, and the tools used. And then from there, we create a class for our equipment monitoring agent. We specify the supported types, and then we initialize this AI agent with the name of the model. And then here we specify that this is a chat anthropic model, and then here we sort of like set that pydantic output parser as the structure of the output that we want to be able to provide as a response. And then here we create the prompt template, which you're going to see down here shortly. And then here we define the tools that this AI agent is able to use. So again, you see we've got the get material availability tool, and get machine states tool, which are the tools that we have imported here from our LangChain tools. So from the equipment monitoring agents, from the tools here, these are the tools that we mapped from our Orchestrator functions. And then we come here, we then define our prompt template, which is the main instructions for our agent here. So basically we're saying you are a batch plant monitoring assistant. Your task is to respond with the material availability and the operational states of machines in our batch plant. To make this determination, you need to check current material availability in all the tanks and then check machine states. Order specific which materials are available in what quantities and in which tanks, which machines are operational or faulty, and then your response must only be JSON. So by giving it this instruction, automatically the LLM will know which tools it needs for which specific request. And then here, because we want to format this in a JSON format, we grab that response that the LLM provides and then we structure it into a JSON. And then this is the function that is invoked by our task manager. So we've got a task manager here. So the task manager is the one that interfaces with the A2A protocol. So whenever a task is sent to this specific AI agent, the task manager is the one that determines, sort of like provides that bridge to then invoke this AI agent here to get the response and then act as an intermediary. So let's jump into the task manager here and see how it does that. So again, here we've got a task manager. So our task manager, again, here you see it implements this in-memory task manager. So basically it gets a user query. So if a user sort of like sends a message directly to this agent, it will get the query, extract this query here, and then here on send task, right? So this is the logic for handling a task. And then here it will invoke this LangChain agent, that invoke method of the LangChain agent, and then it grabs the result into this text, and then it provides that as the response using the A2A protocol. So this acts as an interface between our A2A protocol and the actual execution of our LangChain agent. Okay, so this is pretty much the same that we're doing for the material calculating agent. As you can see, it's got a main entry function, it's got an agent. Again, this is a LangChain agent, and basically this one, the tools here are basically a connection to the database. So we've got a database access file here, which is again a basic Python script that performs this query, select so much so. After being given a product name, it will go into the database, then calculate, get the product recipes, raw materials, the products, and then returns all of that information. So here it returns the material name, tank number, and the quantity of the product. So we've got a tools module here, again, that maps these database data access tools into a LangChain tools. And then if we go into our main agent file here, this is where we then create this tool calling agent, and then we import these get product tools, these LangChain tools, as the tools for this agent. Again, here we define the structure of the response. So we want the material requirements, and then we also want to know what tools were used. And then we create a class for our material calculating agent. Again, we do the same initialization. And then here, this is the prompt template. So again, here we're specifying you are a batch plant production assistant. Your task is to calculate the amount of material that is required to produce a specified number of batches. And then we let it know how it needs to sort of like do that calculation. First, get the product details to understand material requirements to produce a batch. Using that information and the number of batches we want to produce, calculate the total requirements, provide a clear response, and then we give it instructions about what it needs to be specific about. And then we do the same thing. We extract the JSON payload, and then we've got this invoke function that is then called by its task manager. So each agent has got its own task manager module, which is an implementation of the task manager that we created under the shared models. And then from there, we've got this main function. Right, and then we've got the orchestrator agent. So the orchestrator agent, as you can see, is slightly different because it does not have direct connection to the tools. Instead, these two other agents are its tools. So here again, it's also got a main entry function. It runs on port 4003. The material calculation agent, by the way, it runs on port 4003, and then this one runs on port 004. And then we've got an agent connect module. So basically, this is an agent. This is a module that allows this orchestrator agent to be able to connect to the registry, sort of like to discover what AI agents have registered themselves and then know about this capability. So like any agent can do this. The equipment monitoring agent can also be able to discover all the other agents, including the orchestrator agent. But for this demo, we're using the orchestrator agent as the only one that is has got the ability to discover what AI agents have been registered. So it uses what is called an agent connector, right? And then it's able to send tasks to those AI agents using this payload, which is, if you notice here, it's actually an RPC message format. It's a JSON RPC 2.0 message format that includes an ID, session ID, and message. And then we go into our main AI agent here, which is the orchestrator agent. And then here, because this is the AI agent that we want to sort of like interface with the user, we want to know the final decision on whether, if we ask if we should proceed with production, it should let us know what this decision is. What is the reasoning behind this decision? Let us know if there are sufficient materials or not. It must give us a list of the machine state so that we can verify that it actually arrived at a very correct decision. It also needs to let us know what materials are available, and it needs to specify what tools it used. So again, you will notice that it is using the same Claude LLM as our sort of like brains of this agent. And then it has got a prompt template, and then it has got tools that are then assigned to it here, including the LLM and the prompt. And then if we go to our create tools here, so basically these are the tools. So if you notice on the other two agents, we've got a separate module for the tools, but here for the tools, we're using this list agents, which is what it gets from the tool connector. So from this agent connect, it connects, and then it gets a list of agents, and then it lists those agents as tools here within the AI agent itself. And then here I've got a prompt template. So basically, we're telling this that you are an orchestrator agent for batch planning. Your job is to determine if the plant can produce a specified number of batches for a given product, right? And then here we say always use delegate task tool twice to gather information. First, delegate to material calculating agent to calculate material requirements. Second, delegate to equipment monitoring agent to check material availability. And then format the delegate tasks, and then we specify how we should format that information. After receiving response from both agents, analyze the data and make a decision. Your final output must be only a valid JSON object. And then we specify, we give it an example here on how it should sort of like format that response, and then we tell it what not to include. And then this is the function for delegating the tasks. So this is the specific function that allows this AI agent to be able to call these tools when and if it deems fit to do so. And then we extract JSON from text. So these are all the different functions that are acting as a fail-safe mechanism for this specific AI agent. And then here, most importantly, we've got this invoke function which runs this AI agent. And then here, the task manager is actually in this module as a class. So as you can see, this class, we've got the orchestrator task manager, which is pretty much an implementation that is more or less similar to what the task manager of the standalone AI agents, equipment monitoring, and the material calculating. So basically, again, here we're checking the status, the health status of the AI agents, and then we're getting the user text. On send task, this is what needs to happen. Let's finally look at our app. So basically, our app is a command line interface. When it starts up, it simply prompts the user, how can I help you? And then it strips that query, and then it sends that as a JSON RPC message to whatever server you point it to. So when it starts up, when you run this agent, you're going to specify which server it needs to point to. but by default it will fall on this. So for the demo, we're actually going to manually point it to the different AI agents that we want to send the message to. Okay, so this is our code for our multi-agent system. Now let's go ahead and see the demo. Okay, so I've got my AI agents set up here and ready to run. So here I've got my equipment monitoring agent, which is an AI agent that monitors the availability of materials in all of our 3 tanks. It also checks the states of our production machines. And then here I've got a material calculating agent, which is an AI agent that accesses our database and pulls out the product recipes and checks how much material is required to produce a certain number of batches of a given product. And then here I've got the Orchestrator agent. So this is the AI agent that delegates tasks to the equipment monitoring agent and the material calculating agent based on what the user is requesting. Okay, so I'll go ahead and run my equipment monitoring agent. Okay, so as you can see, my equipment monitoring agent is running at port 40002. Now I'll go ahead and run my material calculating agent. Okay, my material calculating agent is now running at port 40003. And then I'll run the Orchestrator agent. Okay, now what has happened here is that the Orchestrator agent is running and it has discovered these 2 AI agents using the A2A agent card. So it now knows the capabilities and skills of these 2 AI agents. Okay, and then the last one is my user facing application. So this is also an A2A client. Now, as you can see here, I can specify which A2A server I want this user client to connect to. So I'll go ahead and start by connecting to the equipment monitoring agent directly. Okay, so now I'm going to ask, what is the material availability and the states of machines in our plant? Now, when I do that, you notice that this message is now packaged as a JSON RPC request, and it is sent to the equipment monitoring agent. Now, as you can see the response where it says, the agent says, and then it gives me a JSON that says the mixer state is running, reactor state is running, filler state is idle, and then it gives me the material quantities for the tank levels, tank level 1, tank level 2, and tank level 3. So these are all available via an Office UA server, which is exposed as a tool using the LangChain framework. Now I want to point it to the material calculating agent. So I'll direct it to port 40003. And then here I'll ask a question like, how much material do I need to produce 5 batches of product A? And then again, it packages that into a JSON RPC request and then sends that to the material calculating agent, which receives it and then it responds. So as you can see here, it says material requirements. It calculates the material 1. This is how much is needed, 4,500. For material 2, this is how much is needed. That is how much is needed. And then it also specifies the tools that it used to get that information. Okay, so now you can see these AI agents exchanging messages using the A2A protocol. And then now I'm going to connect it to the Orchestrator AI agent, which is running at port 40004. Okay, now to the Orchestrator agent, now I can ask a question like, can I produce 4 batches of product A. Now, the orchestrator agent will take this query, and then it has got instructions on exactly how to make a determination of whether one can proceed with production or not. So it will ask the material calculating agent to tell us how much material is needed, and then it will ask the equipment monitoring agent on what material is available and which machines are down, and then from there it will do a calculation and give us a go or no go indication. So when I do that, you will notice that the orchestrator is now calling these two AI agents. Okay, so we've got a timeout on the client application, but let's analyze the response from the orchestrator agent. As you can see, the orchestrator agent now has responded with a decision to say yes, and then it's got the reasoning here that says based on the data from the child agents, there are sufficient materials in all tanks and the required equipment is operational. And then it tells us what are the material requirements, and then these are well below tank levels: tank 1, tank 2, tank 3. All essential machines are either running or idle and ready for use. So the answer here is sufficient materials true. Machine state, it tells us the machine states, and then it gives us the response. Okay, so for some reason the client application was waiting too long to get the answer, and then it timed out, so I didn't put a long enough timeout. So let's give it another go to show you what the response looks like on the user side. Okay, so now as you can see, our user-facing application didn't time out, so we got the response from the orchestrator agent. So as you can see, the response there, it says decision yes, and the reasoning: based on the data from child agents, we have sufficient material and operational equipment. Material requirements for 4 batches are well within current availability, and all critical machines are either running or idle, which means they're ready to use. And we've got sufficient materials, true, machine states, and then kind of like list the states of the machine, and then list the material availability, and then it specifies which tools were used. So if you notice here, the material calculating agent and the equipment monitoring agent are listed as tools that have been used by this orchestrating agent. So now we've successfully built a multi-agent ecosystem of AI agents that exchange information using A2A protocol. And that brings us to the end of this 5-part series on building agentic AI for industrial systems. I hope this has given you the knowledge and inspiration to start building your own industrial AI agents. If you found it helpful, make sure to like, share, and subscribe, and stay tuned for more tutorials on industrial data and AI right here on this channel. See you in the next one.